Welcome back. We're going to press forward in our mini-series on how to estimate stated preference choice models. And in this video, we're going to cover stated probabilistic choice models, which are a generalization of both rank-ordered and discrete choice models. So in these models, the respondents report probabilities or percent chances, and then we need to figure out how do we actually get preference estimates from this type of data. So as I just said, we're observing a probability instead of an indicator that an option was chosen or a ranking. And in an earlier video, we kind of touched on what this probability might communicate or what sort of information it represents. Why would someone be uncertain about the final choice they would make? Well, we talk about this in terms of what's called resolvable uncertainty, which just means that the person isn't exactly sure which option they would choose under the specified scenario because there's some states of the world that will be realized between the time they're reporting this probability to the researcher and the time they would actually make the choice. So what's an example of this? I might ask you, are you going to go for Mexican or Thai food on Friday night? And you will say, well, I'm not sure what mood I'll be in that day, but probably I would go for Mexican food. And then I could say, well, what do you mean by probably? And then you could say a 78% chance. And if you're sure that there's no uncertainty that you're definitely going to go for Mexican food, then you can report P equal 1 or P equals 0 if you're sure you don't want to do Mexican food. So now let's talk about how to estimate these models. We have a variable, a y variable, that is continuous and ranges from 0 to 1, but does not go outside of the unit interval. So the trick to doing this is we're going to invert the logit formula, and I'll walk through how to do this. But as an example, let's look at the binary logit. So we know what the choice probability formula is for that. And what we're going to do is we're going to compare this formula with its complement, 1 minus p. And what we can notice is that the denominators are the same. So if we take the ratio of these two equations, the denominators will cancel, and then we'll be left with just the numerator remaining. And then we can take the log of both sides. That'll give us a function of the z's and gamma on the right-hand side, and then we have what's known as the log odds ratio on the left-hand side. So now this looks somewhat like a regression model. We don't have an error term yet, and we have a weird transformation of our y variable, but this is easily computable as long as p is not equal to 0 or 1 exactly. Now I wanted to talk a little bit about how these stated probabilities provide more information than a straight discrete choice or rank ordering. And let's consider the following set of responses that could all be equal in the sense that they could all be consistent with one another. So let's suppose that if it was a discrete choice, the respondent would choose option B. If it was rank ordering, they would rank B the highest, but then A and then C. And then we could think of two different versions of the stated choice probability. One where B is going to be chosen 99% of the time, A 1% of the time, and C never. Or one where B and A are nearly indifferent, and then C is never chosen. So hopefully you can see that there's differing levels of information in the two different stated choice probability situations, even though each of these is consistent with the same rank ordering, which is consistent with the discrete choice. So in this sense, the stated choice probability framework is a generalization of rank ordering, which is a generalization of discrete choice. And in this sense, we can also think of the discrete choice as being the stated probability situation where we have 100% on the chosen alternative and zeros on the non-chosen alternatives. But as I alluded to earlier, the choice probabilities should be within the open unit interval, meaning they should never exactly equal 0 or 1 because that would mess up the log odds formula. So how are we going to handle it if there's measurement error and people actually do report 0 or 1 or some other rule of thumb interval like 25 or 75? So because we have people answering these questions, they're not necessarily going to say, well, I'm going to choose option C with probability 0.7832. They're probably going to round to 80%. Or 75%. And this really gets tricky when it's in the tail, where we have something close to 0 or close to 100, because that's where the base rate is so tiny that these things really matter a lot. So the log odds is undefined, as I was saying earlier, if p equals 0 or 1. And so what we have to do here is we have to recode these zeros or ones to be very small values. But then this might contaminate our analysis if we're taking these preferences or these stated probabilities at face value. And so to avoid this bias from this measurement error, we should actually be estimating median regression instead of mean regression, or OLS. So we're going to use least absolute deviations, which is another word for median regression. And so our new equation, we're going to put in p tilde, meaning we recoded some of these close to 0 or close to 1 numbers. And then we're going to add this term eta I1, which is going to be the difference in the measurement errors. So how would estimation work if I have more than 2 options? Well, now I instead of having a system of 2 equations, or a single equation, then I'm going to have a system of multiple equations depending on how big J is, because we're going to have 3 observations per scenario. And then when we take the quotients to get the denominators to cancel out, we're going to have capital J minus 1 remaining equations. So if we have J equal 3, then I'm going to have 2 equations. And I'm going to normalize with respect to P2 and difference with respect to Z2. And then I'm going to have this as my system of equations. And I say system of equations, but we're estimating the same gamma. And so what this really amounts to is just more observations per person per scenario. So if I have n people and they each make t choices or face t scenarios, then my data is going to have nt times j minus 1 rows. And it would look something like this. Again, this is the same type of thing I showed in the previous video. Now I have probabilities instead of rank orderings or discrete choices. And then because I'm normalizing with respect to alternative B, it's going to have an undefined log odds. And it's also going to have a 0 for the zj minus zb. And I shouldn't say it's undefined, but it's going to be 0 here. And so we can express these different z's and these log odds ratios as new variables. So I'm just literally taking this information and transforming it in the way that you see in the column header. Same thing with the z's. And so we're going to have information from 2 alternatives per scenario per person. And we would drop the rows for alternative B and then just estimate our model using LAD. And then that would give us estimates of gamma hat. Those are going to be the preference parameters. And then we can do welfare calculations or willingness to pay calculations or whatever we want to do after that. So those are the mechanics of how to estimate data that was collected under this stated choice probability framework. In our last video coming up, we'll talk about how we can leverage the panel nature of the data to estimate highly flexible preference heterogeneity and how that can make a lot of difference to our end conclusions. Hopefully you're looking forward to that. I know I am, and I hope to see you there.